So we did a fluids dissection of an accordion. Here is an assembly of the accordion.
Here you can see an explosion of the accordion assembly. The key components are the bellows, the reed blocks, the end plates, and the valve assemblies. The disassembly process was simple, as the entire object was held together by 4 mounting screws on each end plate. It should be noted that the interior reed assembly was found to be separated from the rest of the structure and badly damaged. Here is an animation of the accordion in operation. When a musician either compresses or expands the bellows, they can press on a key, which opens a set of 4 valves. Each valve is connected to a single reed that plays a single note. By opening multiple valves with a single key press, the notes are combined to form a musical chord. The musician can also choose to selectively block off a column of valves with a toggle, adjusting the number of notes in each chord.
The bass register on a button accordion is a simple mechanical switch that changes which bass reeds sound when you press the left-hand buttons. In a compact instrument with 6 bass reeds, as is the case with the dissected accordion, each button normally activates 1 low bass reed and 1 chord reed. The register switch controls a small wooden piece inside the bass end that opens or blocks the air valves leading to these reeds. In one position, air flows to both bass and chord reeds in the end plate for a full, rich sound. In the other position, the wooden piece blocks the chord reeds so the air passes through the single bass reeds only, giving a cleaner, lighter response.
This is the reed block. Air flows from the bellows to the reed block into the chambers, vibrating the reeds on the end plates and exiting through the tone holes. Keys on the ends of the plate of the accordion control valves that will either cover or open holes in the tone holes, adjusting the notes, producing different notes and sounds from the accordion.
Inside an accordion, the motion of the bellows creates a complex pattern of airflow that can be described using streamlines, which show the direction of the moving air. When the bellows are pushed in, the pressure inside rises and forces air through selected reed chambers. This creates high-pressure regions near the compressed bellows and low-pressure regions where the air exits past the reeds. When the bellows are pulled open, internal pressure drops, drawing air through the reeds. As the air travels through narrow chambers and around sharp internal corners, these streamlines may bend or even separate from the walls, creating small zones of turbulence or recirculating flow. Such separation happens when the air cannot easily follow a sudden change in direction, and it can slightly affect how quickly and efficiently the reeds vibrate.
Now I'm going to look at the accordion using fluid mechanics. The bellows act like a variable control volume. When the player squeezes them, they apply a force over the bellows area, which creates a pressure rise. So the pressure difference driving the flow is approximately the force divided by the bellows area. That pressure is what forces air in and out of the instrument. Once the valve is opened, air moves from high pressure in the bellows to ambient pressure at the gap. Applying Bernoulli between the bellows and the gap gives us a velocity based on the pressure difference. Multiplying that velocity by the opening area will give us the flow rate, and loss from turbulence is absorbed into the discharge coefficient shown in the equation. At the reed opening, the gap size changes in time as the reed vibrates, so the flow rate becomes time dependent. We can use the same Bernoulli-based relationship, but now the area is changing while the instrument is being played. We can estimate jet speed at the gap and calculate a Reynolds number based on the hydraulic diameter. The resulting Reynolds number is large, which means that the flow is turbulent, which helps energy transfer to the reed and produces a stronger sound. Here's the reasoning behind our main assumptions. First, we treat the air as incompressible. Even when you squeeze the bellows hard, the air speeds are far below the speed of sound, so density barely changes. Second, we assume uniform pressure inside the bellows. The volume is small and the air mixes faster than the bellows move, so pressure differences inside equalize quickly. Third, we use quasi-steady flow through the reeds and the valves. The flow is unsteady over a note, but at each moment it behaves like a steady Bernoulli flow through a small opening. Finally, we don't model turbulence directly, because its effects are absorbed into the discharge coefficient, which represents losses near the openings.
So for the qualitative overview, air flows across thin metal reeds. A key opens a valve that allows air to flow through a specific reed chamber. When a change in pressure happens, it causes airflow to go through the slot, and the reed experiences loading that moves the thin metal strips. The airflow bends the reeds into the slot, reducing airflow, which gives it a choking effect. The vibration modulates the airflow, generating pressure waves, which gives it the unique sounds. For mathematical equations, to find the flow rate, we can use Q equals 1/2 rho v squared, and then a higher airflow velocity equals a louder sound. And then to make different sounds, we can use this equation to find frequency. And a higher frequency equals higher pitch, and to increase frequency / pitch, we need to decrease the length or increase thickness of the metal reeds. For example, we calculated the frequency for one of the reeds with the equation, and calculating this, we got the frequency to equal 432 hertz, and that's equal to an 8 key.